Okay. So yesterday we left three topics from the meshing. So we'll just cover that and then we'll move to the next part. Okay. So let me check if recording is started. Yeah. So as I already explained yesterday, so if you have any unnecessary, embossing or something on your model, and without making change in the model, you can neglect it and you can just create a mesh directly. Okay, so for that you need to take a pinch command. So right click on mesh, insert, and you need to take this pinch option. Now in the pinch, we have to do the two selections over here first. So before that, I'll just show you the box selection. So here in the mode, if you see, we have two options: single select and box select. Okay, so when I click on box select, by default we are in single select mode. Now change it to box select, and in the box selection, what happens now? My selection filter is on faces. So whichever faces are coming completely inside the box, those will be selected. Okay, and when I'm doing from left to right selection, okay, only in that case this will happen. Whichever faces which are completely coming inside the box, those will be selected. As you can see, only the face which is coming inside, let's say this one face, only that will be selected. Okay, and when you are doing from right to left, whichever face, even if it is partially coming inside, that will also get selected. Okay, so that is what left to right and right to left selection. So here we are going to use that selection to select this uh, component over here. So first we need to select a primary selection, in which we need to go for edge selection, and we need to select all the lower edge loops of this alphabet. Okay, so as you can see, I have selected it. Click on apply and then select the top edge loop in the secondary geometry. Okay, like this. So I'm making a selection from left to right. Whichever the edges will completely come inside that box, those will be selected. Say apply, it is done. Then you can give any tolerance over here. So let's say I'm giving tolerance should be more than the height of this group. Okay, so let's say I given 5 mm over here and click on generate mesh. Okay, I think size is too large. Let's try with 3. Yes. Here you can see mesh is created and that alphabet is removed. Now you will not be able to see that part over here, as you can see. Okay, so that will be neglected directly without making any changes in the geometry. Okay, so that is how we can use the pinch command. And then next we have, that is match control. Okay, so in the match control, now the case is somewhere like you need to use the symmetry. Why we need to use the symmetry? To reduce the mesh count and to get the faster solution, we go with the symmetry model, right? So what exactly we do in symmetry model? What are the complete cylinder? So let's consider this as a complete cylinder, and we have removed the three we have cut into the two parts. Okay, two identical parts. When you are taking a cut at the middle, you will be able to see that it will be divided into two identical parts. So we neglect one and we consider only one. Now that half part, that also if we divide in between, then those two quarters, they will also identical to each other, right? So with the help of this, we can reduce the mesh count and we can solve the problem faster way. So that is where we need to use the symmetry mesh, right? So here in this case, what you can see, now I have created a mesh over here, and I can see it looks something like this. Okay, so it is something like this. So here you can see the mesh is created denser on this face, and here it is not a denser one. So what I need to do is I wanted to copy this mesh from this face to this face. Okay, it should be like completely mirrored one. It should not be like you know just created a same setting with the same settings what we have applied. So for that we need to use the match control option. So go to the mesh, insert and match control. Then here you need to select a high geometry selection, means this face, and then here you need to select low geometry selection, the face or target face. Okay, and in axis of rotation we need to select the axis of this cylinder. Okay, now in this case we cannot select any axis. We need to create a coordinate system in a such a way that z axis of that coordinate system will be along the axis of the cylinder. So for that, right click on this coordinate system, insert new coordinate system. With what name we are creating it? Coordinate system 5. Select the geometry location. So let's say I'm selecting this face, so it will be exactly created at the along the axis of that particular, right? But it's created in a such a way that if you see this is y axis. Okay, this is a y axis and this is z axis. So we need to align the z axis with the along the axis of the cylinder. So for that, change this axis y and define by global. So global, sorry, it's here, it should be z axis we need to define as a global y axis. As you can see, when I changed, now it is turned in the vertical direction, so it is changed. And then we got the this along the axis of the cylinder. Then right click on mesh and simply generate the then select this match control and then select this coordinate system which we have created, that is coordinate system 5, and we'll just right click on mesh and generate the mesh over here. Okay, so you can see it will create a mesh over here very easily. As you can see, it will copy the same kind of mesh, or it will just create a same mirror of it. Okay, as you can see, that is what match control. And then the last option, that is mesh copy. Now in this case we need two identical bodies. How we can create identical bodies? With the help of mirror command. So here in this case we need to use the mirror command to create the identical bodies. Okay, so whenever the bodies are created with the help of mirror command, then only we can use this mesh copy option. Okay, so these are the very specific cases where we can use those kind of options over there. Okay, so in this case, as you can see, I'll just suppress this and I'll generate a mesh. Okay, so mesh is created, as you can see. Now I wanted to copy mesh from this cylinder to this cylinder. Okay, and for that you need to take a mesh copy option. So go to the mesh, insert and take mesh copy, and here source anchor means select any one face of this cylinder. Let's say I'm selecting this, and select the same face of other cylinder. Okay, so from where you need to copy, that is your source anchor, and target anchor is where you wanted to copy. So right click on mesh and generate mesh. So you can see it will automatically copy this mesh from this cylinder to this cylinder. Okay. Okay, I hope with this all the mesh settings are pretty clear to you, and we have completed this. Is there any question even in yesterday's part, whatever we have seen?
Apparently, no, Kailas. I think we can go ahead.
Okay, I'll request to practice this tutorials, whichever I have shared with you. I'll just show you how you can access those tutorials. So I have shared you a folder and with the name Ansys Training, and if you see inside that, you will get to see the space climb folder, meshing folder, mechanical, and fluent. These four folders. So in each folder, what you will get is you will get a lectures training. you will get a input files, and you will get a workshop instructions training. Lectures is some like theoretical part is explained. Let's say we have seen the repair part. So what are the repair options are available, how we can use, so that is being explained in this theoretical part. Okay, so let's see. Okay, it you can see, and it's showing all the repair options, how you can start with it, what are the file formats supported, and how you can change the settings, how you can go for this repair CAD cleanup, what are the options available, and with the help of which option, and what all those things you can do, all those things are explained over here. Okay, so this is a theory, and then uh, like you can refer this theoretical part. Then you have workshop instructions training, where you will be having a complete guided workshop. Let's say you wanted to do repair, geometry repair, and then for that we have this workshop of this turbocharger or for this particular problem. Okay, so here which geometry, now for this workshop, which geometry you need, hoover underscore geom dot scdoc, this geometry you need to import. Where you will get that geometry? In this folder, that is workshop input files. Let's say it will be in mm, maybe in the model 3. Yes, this is a overjom scdoc. This is your file that you need to import. You can check out the preview as well over here. Here you can see, right? So this preview is also given, and this file you need to open it, and then you can follow these steps. Okay, you need to go to the repair, and repair, go to the stitch option, then just click on this green tick to complete the stitch, and then go for the next option for missing faces, then to create new faces, all those things, all the steps have been explained very well over here. You can practice that. Since we have time limitation, we cannot cover all this part, right? But definitely it is there for your practice. So just practice this, and definitely that will be going to helpful for you. You can see we have done this workshop. For this also I have taken this turbocharger x underscore t, that is a parasolid file format. So you have to import this file, then you have to check out the things, then check for the interfaces, gaps, all those things. So how you can repair it, all the things are given. Okay, so this is how you need to access this folder. All the things are given for all. Like let's say for Speclim it is there, for meshing also it is there. You have this workshop instructions for FASCFD, then we have you this input files, and then lectures training, different mesh method, global mesh control, local mesh control, whatever we have seen, same options or same things are being there in the documentation. Okay, then in the mechanical side also you will be able to see this folder where you have the lectures, instruction training, then we have this workshop input files, and then workshop instructions. It's like you can just use any of this, how to do that particular workshop. So all the steps are given, what is the goal of that, what assumptions or what is the problem statement you are making, then how you need to start solving that problem. So all the steps have been given very well. Practice that, and definitely that will be helpful. So with this I have shared all the content, so you can just take a benefit of that. Okay, okay, so we'll start with the next. Yes, so now what we'll do is, now you understood the geometry, you understood the geometry cleaner, then meshing part. Now what we'll do, we'll solve a complete problem from start to end for a mechanical side, right? So for that you need to take a analysis system. So I'll just expand the analysis system, and in this, for the static problem, so in the mechanical we need to take this static structural analysis system. So drag this and drop it over here. As you can see, this is the analysis system what we get. Okay, now in this you will see first step, that is engineering data, then geometry, model, setup, solution, and result. So we need to complete all these steps to complete a simulation. Okay, so first step is engineering data. Next to that, if you see there, it is automatically showing as a green tick. What it means, if I'll double click over here, you'll be able to understand that in the engineering data you need to add a material first, okay, in the mechanical problems, okay. And when I'm opening this engineering data, you just need to double click over here, and when you open it you'll be able to see structural steel, okay, which is a default material over here. Means, though you are not adding material, then you can say structural steel will be available by default, okay. So no need to make any changes in that, and you can start solving the problem with the structural steel, right. Then here in the structural steel side, you can see the properties of structural steel. Over here you can see its density, then isotropic properties like Young's modulus, Poisson's ratio, bulk modulus, all the things you can check out over here. Whichever properties you cannot edit, those will be calculated from the given data. But here you can see you can edit the Young's modulus, you can edit the Poisson's ratio, you can edit the thermal expansion coefficient, then you can edit the density, whichever, okay, all these properties you can edit it over here, correct. And then with the help of this you can easily um, we easily change the properties whichever are required. Now in this case, if you wanted to add any new material, now this is a default material that is available over here, right, which is a structural steel. Let's say if you wanted to add another material, then you have to go to this engineering data sources over here, okay. So click on engineering data sources, and in this engineering data sources you will be able to see the different categories of the material. Here you can see general material, then you have additive manufacturing materials, geomechanical, composites, non-linear, explicit, hyperelastic. So different material categories are available over here, okay. Whatever category you select from this, let's say I'm selecting the general materials. It's taking time. Okay, and when I'm selecting a general material, so in the outline of this general material, okay, you will be able to see various materials. Okay, in the general materials we have almost 12 to 13 materials available over here. So let's say I wanted to add a material, that is aluminum alloy. So what you need to do is, to add a material you just need to click on this plus sign. Okay, when you click on plus sign, this book option, it shows that this material is added for the current project. From, means like what we are saying is, from the Ansys library we are calling that material for the current problem, okay, which we are going to solve for, okay. Then let's say if I wanted to add another material, that is copper alloy, so just click on copper alloy in the on the plus sign. You can see with this also this is added. On the bottom side here you can just check out this materials properties, okay. You can check out what are the material properties are there for that particular material. Here you cannot edit these properties, okay. You cannot edit these properties. You, this is a Ansys library, you can just call that material into the local current project, and there you can edit the material properties. But from the library itself directly you cannot edit it. Now I have called these two materials, one is aluminum alloy and second one is a copper alloy, right. So just again click on engineering data sources to go back to the current library. It's like current project library. Here you can see we have added this material twice. I'll just delete it once, we'll keep two one. Okay, so you can see now copper alloy and aluminum alloy, these two materials are added over here. Okay, so here you can see now this material and their properties. Now here I can edit this. Why? I have called this materials to the current project library now, and here I can definitely edit its properties, right. So that is how we can you know go for the adding new materials, and we can easily change the material properties over here, okay. Similarly for aluminum alloy also it can be done. Then structural steel also it is possible. So for all you can edit the material properties only when you are calling that material for the current project. It's when you're taking that material from the library, then only you can edit it. Inside the library itself it is not possible to edit the material properties, okay. So this is about the materials which are present over there. What if I wanted to create a material which is not available in the Ansys, right? It is possible that I am working on doing a research on some kind of material, and I wanted to do the it's testing for some purpose, right? It is not necessary that material will be available in the Ansys library. So in that case, what we can do is, here you can see a option. Click here to add a new material. Okay. When you click over there, you'll be entering it to the name edit mode. Here I can give name of the material. Let's say I'm giving name as ABC. This is my new material. I have not defined it, so I am just naming it as a ABC because I have not given any name to that, right? So I have given the name. Then on the left side in the toolbox, you can see various material properties which you wanted to add. Let's say I wanted to add bilinear isotropic hardening properties. Double click on it, it will be added over here. And if you see over here, whatever the yellow highlighted part, that is the minimum input condition that we need to give over here. Okay, so as you can see, first one is the Young's modulus. So let's say I'll give 7 e raised to uh, 10. Okay, that is my Young's modulus. And it is given, property is given. Let's say I'm giving Poisson's ratio of 0.2. Then let's say we are giving the mm, yield strength. Okay. Okay, so we are giving let's say 2 e raised to 8 or something, tangent modulus something you can give. Okay, so when you define all the property, I have given random properties, so don't consider this. I'm just showing how you can define the material. So when you are creating your own material, you will be having its properties with you, right? So you can define those properties, and you can see when I'll define complete properties, this question mark, there was a question mark. If I don't know if I can delete. If I delete this, now you can see there is a question mark. So when you fully define a material, the question mark will go off, and then you can say now this material is completely defined. So this way you can define any new material, and you can use it for your research purpose. Okay, I don't want it, I'll delete it. Another way to add of adding new material is select any existing material, right click on it and click on duplicate. So it will be duplicated. You can change its name, let's say XYZ. Okay, and you can change the properties here. Okay, whatever you need, you can edit it and you can change it. Okay, that also helps you to create a new material. So both way you can create a new material over there. Okay, I hope it is clear to you. Like here we have added three materials. One is structural steel, aluminum alloy and copper alloy. Okay, then once this is done, you have to close this engineering data. Click on this close, so it will close the engineering data, and you will be able to see uh, okay, the material is added, and next step is to go to the geometry where we need to create a model. So launch the space claim, and then we can create a model over here. Okay, so it's launching the space claim, so need to wait. Okay, so it is open now, and we can add the, we can create a model. So let's say I'll create a very simple model. Just 1 second. Okay, so we need to create a model. Let's say I'll create it of 20 by 20 dimensions. Okay, and return to 3. And let's pull it for let's say 250 dimension. Now we'll create a no, simple beam structure. Okay, and then we'll observe the stresses or deformation on that particular model. So we'll add two different columns. This will make it 15 by 15. And again we'll take it for 150 Now it is single body, so I just need to split this body split along this. So you can see there are two separate solids, solid 1 and solid 2, right? Now what I'll be doing, I'll be fixing this on both the ends, and I'll apply some load at this specific point. Okay, so that is what we need to do. So when there is this kind of model, you need to share the topology. So go to the this model, and okay, you need to give the bounded connection over there. Okay, so that will do in this mechanical part. So once the model is ready, go back to the workbench and launch the model over here. Okay, it's just launching the model here. Okay, I can see model is imported. Now this is one window where we can do a complete process from assigning the material till the solution or results. Okay, so main mechanical, it is very simple to do these things. Okay, now you can see the geometry. Okay, there are two models. One is a solid one and solid and solid, right? So for the first model, let's say we wanted to assign the material. So in the geometry, you can see this material name over there in the details of that particular solid. If you see the material here, we have the material that is structural steel, which is the default one. I don't want structural steel. I just let's say I want it as a copper alloy, so I have selected copper alloy. For the second beam, I don't want structural steel. Again, I want it as a aluminum alloy. So you can see name is changed. So for this solid one, it is aluminum alloy. For solid, it is copper alloy. Okay, both the materials are defined, and you will be able to see those names of the material which we have added in the engineering data, those materials over here, along with their complete properties. As you can see over here, you'll be able to see the complete detailed properties of that material here. Okay, and then once this is done, then you can go to the next step, that is mesh. Before that, in the mechanical side, you'll be able to see something that is called as connections. Now in this case, there is a connection in between these two, and that connection is bonded. What is bonded connection? It is a fixed connection. Means there is a joints. Okay, so there are various types of joints available over here. You can see in that we can define the connection between those two. In this now it is a fixed, means what we can say is we have fixed those two models at the on these particular phases, like this phase of beam 1 and this is the phase of beam 2 where it is fixed. Okay, so that you can easily understand from this. Instead of bonded, you can give no separation. What it means, when you are giving no separation, it will allow the rotation, but it will not allow to separate out from it. Okay, that is what rotation. And with a frictionless, it will no it will not allow separation again, and again rotation will be there, but it will be frictionless rotation you can consider. Then we have the rough contact, where we can define the roughness factor, and then frictional also we can define. Okay, so these are the various contacts that we have. In this case, we are going to have this as a bonded contact over here. Done. And then go to the mesh. Now we have to create a mesh for this model, so just create a default mesh first. So I'll just right click on mesh and say generate a mesh. Okay, so default mesh is generated. I don't want it to be this much coarser. Let's say I'll give sizing of 2.5 mm to all the models. Now I am applying this in a global mesh setting. So what it means, it will be applicable to both the models. So just right click on mesh and generate the mesh. Yeah. So you can see mesh is created. You can see very good quality mesh is created over here. Okay, and then what we can do is, let's say we'll fix it on this end and we'll apply some compressive load from this side. Okay, and then we'll see how the results are changing. Okay, or compressive or a downward force also we can apply. Okay, mesh is created. I can keep on adding the mesh count. Okay, I can keep on increasing. That will increase the solution accuracy, as well as it will take more solution time as well. So let's say I'll just improve it little further, but I'll not improve too much, so that it will take more time. It should not take more time to get the solution, right? So let's make it as 1.25, and you can say it is pretty we can say finer mesh what we get over here. Okay, and for standard shape, getting a good quality mesh is not a big challenge. Okay, so if you see here, you will have a good quality, that is one throughout the model. There is aspect ratio of 1 is possible here. Then skewness of maximum, it is 0. You can say it is in 10 raised to minus power 10. That means it is 0 only, right? It is varying within that range. So it's a very good skewness also what we get, right? So all those things will be there when you are dealing with a model which is which we can say having certain standard shape over there. Okay, then okay, then next is uh, once you create a mesh, then you need to apply the boundary conditions now. Okay, now we have to define the problem, like define the boundary conditions over here. I'll just hide the mesh so that we can see it properly. This is the option to show or hide the mesh. Okay, so first of all, when you see this structural, static structural, okay, so now we have created completed till mesh. If I go back to the workbench, you can see geometry, model, these are coming as a green tick and green tick. Okay, and then setup, it is showing as a question mark. What it means, attention is required. It means you need to give the inputs over there, right? So here I need to give a fixed support on this face, right? So right click on structural steel, insert. Now these, all these, you can see these are the boundary conditions over here. So let's say I wanted to give fixed support. So here we have fixed support option. Select it, select the face where you wanted to apply, and click on apply. So you can see it will be applied. Let's say here we are adding the compressive force, right? Or okay, let's apply it as a compressive force. Okay, then or downward force we can apply. So for that you need to add a force component. So right click on structural, static structural, insert, then force. Okay, and here select the location. Let's say I wanted to apply it to this face in vertically downward direction. So change it from vector to components, and then in negative in downward direction it is minus y. So here give the value. Let's say we are giving 10 kilonewton force in the downward direction. Then you can see whatever the minimum inputs are required, that is done. Then it is asking to update it. If you have further more boundary conditions, you can apply them, otherwise let it be, and just right click on it and solve the problem. Okay, so right click on this static structural and solve the problem. Here you can see the progress. From this you can get this progress bar, which you can track. Once it will complete, solution will be converged. Okay, model is solved. You can see the green tick over here. Okay, you can see the green tick over here. That means problem is solved, and you can see green tick throughout, and results are also done because we have not added any new results. So to add a result, right click on solution, insert, let's say adding deformation, total deformation, then insert stress, equivalent stress. So let's say we'll see these two results over here. So again right click on solution and evaluate all results. Okay, results are calculated. Just click on deformation, so it will show the total deformation over here. You can see just due to grid you are not able to see the coloring. Okay, so this is how the deformation is taking place. If I okay, so you can see this is how much it is deforming from its original shape. Okay, so when it was straight and when we applied 10 kilonewton load in the downward direction, you can see this is how the stresses are sorry, this is how it is deforming, and stresses, this is how the stresses are generating inside the model. So all those things you can observe over here. You can see what is the minimum stress, maximum stress, and average stress value over here in this table. Then you can create animation for this. So for that you just need to click on this animation to play. So let's create it for 10 seconds with 100 frames, and just click on play the animation. So it will play the animation and you'll be able to see this. Just 1 second. Okay, so like this, you can get a deformation animation, you can get a stress animation, you can get a complete detailed result out of it. Okay, you can change its contour whether you want a smooth result or the smooth view or the contour or with wireframe with the elements, how that all those things you can check. Then you can add maximum minimum probe over here, minimum where you are getting the minimum and maximum values, those probes you can add over here. Okay, and then if you wanted to give some annotation at different locations, you can just put that, you can give the note what exactly you wanted to give. Okay, all those things are available. Then you can generate a report out of this. So just to generate the report, you need to go to this file and sorry, home, and here we have a report preview. So you can go to the report preview, it will generate a complete report. Okay, from the material properties, model, everything it will add into the report. Only the results images will not be added over here. First of all, what you can see, okay, results everything will be there except the images. If you want to add the image, you need to add them manually first. Okay, so you can see this is the ascent curve what you are getting, then resistivity graph, then other results, okay. So all the detailed results you can get from this. If you wanted to add any specific result, let's say I wanted to add this deformation graph. Okay, so to add this or this deformation image, just select this image, click on this image and add as a figure. So you can see it will be added over. Similarly for stress also I wanted to add, again add it, and then go to the report preview again and again generate the report. So it will generate the report once again, and then we'll be able to see the complete details. Okay. Mm, okay, so you can see the image of the model, then all the settings what you have applied, from where you have taken the geometry, where it is saved, everything, all the units, what is the xyz minim no, dimensions, its volume, mass, all the details you can get it over here. Okay, you can get a its complete properties, materials, what are the material you have defined, what are the coordinate systems, all the details in the report you can get it. You can structures, that is a5, where is a, this is a5 means what are the boundary conditions you have applied, so all those things also you can check it over here. Okay, on this phase we have applied force of minus 10,000 Newton, right? So all those things it will show you. Then in the solution part, you can just check out the total deformation. um, Here you can see this is the total deformation graph that you are getting over here. What is the minimum, maximum, and average deformation? Then similarly, stress, equivalent stress, minimum, maximum, and average. Now these images are not coming properly. To get it properly, you need to make it something like this, and then you need to take capture the image. Okay, then you will be able to see this images properly. Okay, so this way you can get all these results. You can click on publish to save this result in mst or stm file format, or you can just click on print so that you can save it in text file format. So when you click on print, here you can see you can use any the pdf converter. Okay, and that will help you to convert it into pdf. You can change the font size as well. Okay, as required. Okay, so this is how we can completely solve a problem from start to end and get all the detailed results. Okay, so I hope this is clear to everyone. Is there any doubt in this? Any doubt in the complete mechanical problem?
Okay, Kailash, I think we are good to move
Okay, then we'll move to the next, that is Thermal analysis. Okay. For thermal analysis, for structural analysis, we have taken static structure, whereas for thermal analysis, we need to take steady state thermal. Okay, drag it and drop it over here. Again, go to the engineering database where from where you can add the material. Before that, let's discuss the problem statement first. Okay, so in this, what we need to do is this is a pump housing, and what we need to do over here is we need to analyze this pump housing. Okay, for the heat transfer. Okay, and we need to consider the two materials over here. One is a plastic and second one is a aluminum. Okay, and we need to check the results or the difference for the results for these two cases. Okay, so that is what our aim over here. Okay, then what are the boundary conditions that we are going to consider over here? So first one is the pump housing, which is mounted to a pump. Okay, that is held at a constant temperature of 60 degrees Celsius. Okay, what it means? The outer surface, okay, is sorry, the pump housing is mounted to a pump which is held at a constant temperature of 60 degrees Celsius. This mating surface that has a temperature of 60 degrees Celsius. Okay, and we'll assume that as a surface, that as a mating phase of the pump housing to be which is held at 60 degrees Celsius. Okay, then the interior surface of the pump housing which are held at a temperature of 90 degrees Celsius. That is the inner temperature of this pump house. Okay, and then we are going to take a simplified convection. Okay, there will be convection from the outer surface of the pump housing to the air, right, which is at 20 degrees Celsius. Okay, these are the boundaries that we are going to consider over here. Okay, then go to the, I'll just close this. I hope you understood the problem statement. So I'll just go to the workbench, and then first what we need to do is we need to add two material. One is the aluminum alloy. What material? Aluminum and plastic. Okay, so we'll add two materials over here. Go to the engineering database and then visit this engineering data sources library, and there in the general materials, so we have this aluminum alloy and plastic material. So this is a plastic material that we have here, polyethylene. Okay, so this is a plastic, so add both. So you can see aluminum alloy and polyethylene both are added over here. Okay, done with this, and then again go close this engineering data sources. Okay, and just import the geometry. So right click on geometry, and then import geometry and browse it. So browse the geometry. So go to the mechanical workshop input files, and what geometry we need? Pump housing STP. So this is the file that we need to import it. Select it. Okay, and it will be imported, and then just launch this. Sorry. Yes, so as you can see, this is the pump housing that we have. You can see this model over here. And now we'll go back to the workbench, and here you can see we need to launch the model where we can create a mesh, and then we can apply the various settings and solve the problem. Okay, so model is imported. Now first step here, what we need to do is, let's say we'll solve it with a metal, right? That is aluminum alloy. So what you need to do is select this model and change its material from structural steel to aluminum alloy. Done. And then you can just simply create a mesh for that. Let's say we'll create a default mesh first. Okay, sorry, create and generate a mesh, and then add the sizing. Let's say we'll add sizing of 5. Make sure in which units you are working, that is very important to worry. Okay, right click on mesh and say generate mesh. Okay, mesh is created, but still you can see it looks not that great. So again, make it more finer. Let's make it 3 mm. Right click on mesh and generate the mesh. Okay. Mm, let's make it this 2 mm final and generate it. Okay, model is meshed, and now we are good to create a apply the boundary condition. Now you can see, instead of static structural, now we have steady state thermal. And here, if you right click on it and go to insert, you will be able to see only thermal related boundaries here, right? So first one is a temperature that we need to add, where we need to add temperature on the inner faces, all the inner faces. So you need to make sure to select all the faces. So simplest way to select these faces is select any one face and go to this extend option and say extend to limits. You can see automatically it will select all the edges or all the faces until there is a smooth change. Okay, if there is a sharp corners like this, then it will not select that. So what, that is what we need. We need only inner surface, right? So which is selected, click on apply, and here temperature is 90 degrees Celsius. Temperature unit is in degrees Celsius. If you want to change it, you can go to the unit and you can see it is in uh, Celsius. Okay, if it is in Kelvin, then you can change it to Celsius. Then next, this mating phase, it has a temperature of 60 degrees Celsius. So right click on it, insert temperature. This is another way of applying boundary. You can select the location where you want to apply, then directly right click and insert. But what are these options you can see, those will be available only when you are selected steady state thermal. Okay, then only you'll be able to get this boundaries. Okay, then temperature to, here we have temperature of 60 degrees Celsius added, and then on the outer surface, we have temperature, or sorry, there is a convection from this surface towards the air at 20 degrees Celsius, right? Again, select any face, extend to limit, so it will select all the outer faces, and then right click, insert convection. Okay, so convection is added, you can see over here, and take it no, from the table data. So here click on this arrow and import temperature dependent. Okay, and here we need to select the stagnant air simplified case, say okay to this. Automatically this film coefficient value will be imported. If you don't want to import it, and if you want to give it by your own, that also you can do it. Ambient temperature is 20 degrees Celsius, so change it to 20 degrees Celsius, and that's all. We have given all the boundaries over here. You can see when I select a steady state thermal, you will be able to see three boundaries. One is a temperature of 90 degrees Celsius at A. Where is A? Here. Then there is a temperature of 60 degrees Celsius at B, that is here. And then there is a convection at C, we at 20 degrees Celsius, which is here. Okay, all the boundaries are defined. Then right click on steady state thermal and solve the problem. Okay, it is done, and a problem is solved. Now we are going to find the result, that is solution. Insert, first we'll see the temperature, and then we'll see the total heat flux. Insert thermal, total heat flux. Okay, right click on solution and evaluate all the results here, and you can select the temperature. I'll hide the mesh, oh, so you'll be able to see the results here. Okay, so this is how temperature is varying inside a metal, you can say this motor, what's its name, housing, that pump housing. Okay, when it is of metal, you can see complete heat transfer is taking place from inner surface, which is at you can say the 90 degrees Celsius. You can see maximum is 90. And then how this is how temperature is varying inside, and you can see towards the outside we are getting the maximum heat transfer in this case. Now we need to solve the same problem with another material, that is polyethylene, which is a plastic material. So to do that, we just need to change the material and solve the same problem. So what we can do is, there is a shortcut. You can just click on this arrow, and here you have option to duplicate. So it will duplicate the same problem. Okay, you can see copy of steady state thermal. Okay, then just go to the models again here. Okay, and just need to change the material. So go to the geometry, select this model, change the material to polyethylene, and just simply solve the problem. Everything is same, you just need to solve the problem. Okay, problem is solved. Then select the temperature, and here you can see how the temperature is changing over here. When it is a plastic material, you can see temperature variation or heat transfer from inner surface to outer surface is less due to the plastic material. If it is a metal, you can see how the temperature is varying over here. So that is how you will be getting the um, the results. Okay, so you can, I'm not sure, I'll just try. That is CFD post, correct. Mm. Okay, so is there any doubt in this part? So this is how we can compare the results. We can get a results for both the cases. We can check out we can check out the heat flux as well. So you can view the heat flux in the vectors format as well. So you can just see how we are getting this, heat flux direction. Okay, so all those things you can uh, what I can say you can analyze over here. Okay, you can see. This is how heat flux is taking place. Okay, in both the cases you can see that. Okay, so that is how we can solve a thermal problem. Is there any doubt in that? Hello, am I audible?
Yeah, Kailash, I think we can move forward.
Yeah. Okay, okay. Then we can move to the next part. So we have seen the um, thermal structural analysis. Now we'll see the modal analysis. Okay. So in the modal analysis, we need to take another analysis system, that is modal. Modal analysis is something where we need to find out the different mode shapes where at which there will be maximum excitation, okay, in that particular model, and will be facing the maximum vibrations, right? So that is what modal analysis we need to do. So for that you need to take this modal analysis system, drag it and drop it over. Okay, and here we'll keep the default material, that is structural state, so no need to add new material. You can go to the geometry where you can create a model first. So we'll just create a simple 2D plate over here and then we'll analyze it. Okay, let's create a plate over here. Okay, plate with a hole. Okay, delete the middle surface and done. So we have created a plate. Okay, and let this plate be a 2D plate. Okay, it's a surface body, and then we move to the workbench and launch the model where we can create a mesh and solve the problem. Okay, plate is imported. Now, if you observe one thing next to this geometry, there is a question mark. Why it is there? Because when we are solving any problem in the mechanical side, we need to have a complete details of that, right? Because thickness of the though it is a sheet metal, right? For sheet metals also there will be certain thickness, so we need to define that thickness to get a detail to get a proper results, because depending on the thickness the strength of the model will be changing, right? And for that purpose we should have the this uh, thickness over there. So you can see when I select this surface, here you can see thickness in the details of the surface that is highlighted. That means we have to define certain thickness over there. Now you can see I have defined thickness of 2 mm, and then we got a green tick over here. That's all. Then you can create a mesh. So let's create a mesh with the default mesh settings first. Generate the mesh. Now in this case, uh, you might have seen I have not added the material, not assigned the material. Why? I am using a default material. So if you see, by default the same material will be assigned over here. If you see material here, you can see it is a structural steel, which is by default, because we have not added any new material. So there is only one material available, so that will be by default assigned. Okay, then check the mesh. Now it is 14. Let's make it as 5. Generate the mesh. Okay, still it is not good. Let's make it 2 mm. Okay, still it's not that great. So make it as 1 mm and generate the mesh. Okay, mesh is created, looks pretty good. Still we can, there will be a possibility to improve it, but we will consider this as final mesh. Okay, and we'll move further. Okay. Then now what we need to do is, if you see the model, and in the model now we don't need to apply anything except the fixed supports or the support. Okay, so here you can see model insert, and here you can see maximum conditions are related to support. It's like giving the boundary conditions related to support. So let's say we'll give fixed support on 4 corners. So I'll select points 1, 2, 3, and 4, or for all 4 points are fixed. You can see we got a free fixed support, and there is a option over here for pre-stressed. So where this kind of model can be used, let's solve this, then I'll tell you where this kind of simulation can be done. Okay, so we are not applying any pre-stress condition, and then click on analysis settings. Here you can see maximum mode shapes to find is 6. So it will find out 6 frequencies where you will be able to get a maximum excitation. You can increase the number. Let's say I want it for 8 mode shapes where I will be getting the maximum deformation. Okay, so change it to 8, right click on model and solve the problem. Okay, then solution is completed, and then click on solution. When you select the solution, here you can see in the this graph, it will show you 6 graphs where you are getting the maximum deformation. So these are the frequencies. If you see the tabular data, sorry, 8 results, right? So these are the 8 frequencies where you will be able to get a maximum deformation for the different mode shapes. Okay, so now how to find out the deformation? So for that, right click on these graphs. Now this time we are not going to say like right click here, insert deformation, total deformation. No, here right click on a graphs, select all, again right click on a graph, create mode shape results. You can see automatically the deformation related to each mode shape will be added over here. Then just right click on solution and evaluate all the results. Done. You can see the first mode shape over here, and the frequency or deformation related to first mode shape. I'll just hide this uh, mesh so you can see the result. Now you can see this is how this model is getting excited. If I play the animation, you will be able to see this. It is something like this. In the middle, now it is having the maximum deformation. And what is the maximum value of the deformation? It is 100 mm, that you can check here. Okay, you can have a more detailed animation, like you can give it for 10 seconds with 100 frames, and then you can play this. Okay, so you can see this is how the model is changing its shape. Another thing over here that you can do is you can save this animation. I forgot to tell you in last part, but you can save this animation. Here you have option export video file, and you can save it, let's say on desktop, and with this file.mp4, click on OK. It will solve it for one mode, or it will run it for one mode, and that will be saved. Okay, done. If you see on the desktop, this is the animation, it is saving. Yes, you can see this is how you'll be getting the animation file of it. Okay, then now you can see these results. I'll just close this. Yes. Okay, now this is for mode shape 1. So you can see when we are getting this frequency, when what I can say, it is deflecting exactly from the middle, but when frequency will increase, it will not deflect the same way. Now it will deflect this kind. Okay, when the frequency will reach to 505 hertz, then it will start deflecting this way. I will play it again. I can say like one side is going down and one is going up. This way it is creating the deflection. Okay, this is when frequency is reaching to 505. Stop it. Next, deformation 3. Again check out, it is at 629. Now in this case, it is in a horizontal way, like on opposite, or we can say the other two sides. Previously it was on this side and this side, now it is on this side and this side. Okay, stop this. Then next deformation, you can see it is on all four sides together. like this you can understand it very well. I'll play it again. Okay, so this is how they deform, we can say, at this specific frequency, which one it is, fourth, that is 773.56 hertz. You will be able to see this kind of deformation and maximum excitation this way. Okay, then next one is 1186.9, and then you will be able to see the deflection this way. Okay. Okay. This way we'll be getting the deformations for the different mode shapes. We can see when frequency will be increased. So this is how we can get a results. Now in this case, if you see, there is no pre-stress condition. Okay, we have not given any pre-stressed values over here. Like there is no pre-stress is applied. So in which cases we can use this? Okay, in which cases? Oh, sorry, it just failed. In which problems we can use, for which cases we can use this kind of thing. So maybe you are trying to do the modal analysis of a flight wing or a complete flight or any specific component. You can, if you are working in there is some workshop in that you have some lathe machine or some other machinery component, so there will be maximum vibrations which will be generating, right? So how we can use the dampers and then how we can reduce this vibration. So all those kind of simulation can be done from the model, or there is a another tool also we have. With the help of that you can do this simulation model. Model acoustics can be done, model can be done normally, and then transient uh, dynamics simulation can also be performed. Random vibrations simulation can also be done for those kind of problems. So these are the different ways in which we can get the uh, this kind of simulation can be done for those kind of problems. Okay, so I hope this is clear to you. And um, yes, so that's all for from mechanical side. Is there any question from yesterday's session still here? Is there any doubt? Um, there is no interaction from your side. That is the reason I'm not able to understand if you all are getting whatever I'm teaching or not. That is the big question we have. Is there any doubt?
Kailas, there is one question. If you could explain the difference between structured and unstructured meshes.
Okay, structured mesh is um, something I have already explained yesterday's part. It follows some specific orientation. Okay, in general I'm talking. So it follows a specific orientation, and that helps you to get a a good mapping of the mesh, and that also help you to get the good results throughout the domain. Okay, and whereas if you talk about unstructured mesh, so it is uh, it is not properly placed elements. They are randomly placed. Okay, and but that is required whenever there will be no that is required whenever you have some complex shapes. Okay, in that case you need to go with the unstructured mesh, where creating a structured mesh is very difficult. Okay, in that case you need to go for the unstructured mesh over there. And again in 2D we create a sorry, in 2D we create a quadrilateral elements, and in 3D we create a hexahedral elements for the structured mesh. Okay, And again, for unstructured mesh, we mostly created tetrahedrons or triangular elements in 2D. Okay. Again, structured mesh is something which is recommended for any kind of problem, but it is very difficult to get that kind of mesh for complex shapes. So then in that case, unstructured mesh, we have to go with unstructured. Or there is another thing that you can do is you can go with the hybrid mesh. Okay, so which is partially structured and partially unstructured. Okay.
Yes, Kailas, I think that's any question.
Any further question? Okay, then I think we can move to the next part. So next part is we'll see the CFD. Okay, now I consider that mechanical part is clear to everyone, and then we'll move toward the CFD side. Now we'll have a quick introduction about the CFD, and then in the second half we'll solve the problem on the CFD side. So I don't know if you are uh, from bachelor's or master's. Can someone confirm?
Yes, the participants are diverse, Kailas. So we have from the head of department to the undergraduates.
Okay, okay, okay. So yeah, so you if you have an idea about the CFD, then it will be very easy for you to understand the CFD part. Otherwise, you need to have some basic idea. So I'll just try to quickly make you understand what is CFD, how exactly this CFD works. Okay, and then we will see how we need to solve any problem in the CFD. Okay, so just give me a moment. Okay, so first of all, what is CFD and how does the CFD works? So CFD, that is computational fluid dynamics, which is a science that predicts the fluid flow, heat and mass transfer, other chemical reactions, and other all different fluid related phenomena, right? So to predict these phenomena, CFD solves the equation for conservation of mass, momentum, energy, etc. To the given fluid domain, right? Then what kind of what kind of results that we can get from the CFD simulation? So this CFD simulation that provides the detailed information about the fluid flow behavior in terms of, let's say, the distribution of pressure, velocity, temperature, mass flow rate, etc. Right? So we can get a complete detailed distribution. Then we can get the forces results, like drag force or lift force in case of external flows or aerodynamics problems, or in case of automobile problems, right? Then we get a distribution of multiple phases like gas and liquid phase, gas and solid phase, etc. We get even the species composition like reactions, combustion, pollutants, etc., and many more other things, right? So this CFD, in which stages of the engineering we can say we can use this CFD? So let's say in the conceptual stage, when you are trying to create certain new design, so there you can use CFD. Then in complete detailed product development, we can use the CFD in the optimization stage, and then for troubleshooting, like to understand why certain problem is existing, that for that purpose we can use the CFD. And again, of course, for the redesigning. Now I used to give this example in every session. That this example is of Burj Khalifa, which is one of the tallest building in the world. So if you do little research, you will understand the tip of that building can deflect up to certain limit. Okay, and why it is done or why it is possible. So if you see, in Burj Khalifa, which is located in Dubai, which is a desert area, right? So in the desert area, you'll be able to see there will be a lot of storms, or sandstorms will be coming, and that will be going to hit the tallest building. So definitely the impact will be much higher as compared to any other small buildings over there, right? And to overcome that, they have made such a design so that the tip of that Burj Khalifa can deflect up to certain limit. Okay, and that helps you to not get any stresses generated inside the building, or not getting any damage to the building structure. So that is where CFD is very important. And nowadays we consider that CFD is like, yeah, it's one of the, from the air, it's for aerospace peoples, or for only for mechanical people. No, nowadays CFD is so vast and so important for any kind of department, and it is really helpful now. If you talk about various COVID situations, and I don't know if you are aware, like in the COVID situations, Ansys has done a lot of CFD simulation for the isolation wards, for the O2 concentrators. They have developed various labs as well. Like, what I mean is, it is even very important for healthcare sector. Lot of research is going on, in various operatives, how some tumors can be uh, like removed just by giving certain medicines or something. So that how that is going to help, or whatever our blood is there in a body, how it gets circulated, how the heart pumps the blood, all those things can be easily simulated with the help of CFD. And not just the mechanical or aerospace applications, but it has application in the healthcare, in the electronics, in the civil engineering. So which is which covers a very wide range. And it is very important nowadays. If you see, various companies, starting from the smallest business companies to the largest companies in the world, everyone is acquiring CFD as their important department, where they will do the CFD study on their components, or on whatever areas they are working. So definitely that helps them to get a better design to sustain their product in the market. So definitely CFD is playing a very important and vital role in the today's era. So if you see electrification, now it's like a complete, you might have seen there is a continuous hike in the petroleum prices. So that is also leading towards the EV section, that is electric vehicle section, where we use batteries. And for batteries you can do the CFD simulation, which is also available in ANSYS. So all these things which are very important. Then again, electronic circuits, or the IT labs, or different labs where heat circulation is very important, or we can say heat ventilation is very important. So in all those cases, CFD is very useful, and it's very important topic nowadays, right? So, and now it is again not possible every time to do a testing, and or to perform an experiment for that, right? It is not possible to do the experimentation, or to do the experiment, getting the experimental results, or do the testing, right? So in that case, simulation, that is what makes it more simple to work, and that helps you to get a more accuracy data. So There is That's where CFD analysis that complements the testing and experimentation by reducing the total efforts and the cost required for the experimentation and data acquisition. So you might be knowing, if you take any offshore application or any aerospace application, just if you wanted to do the testing for any specific model, just to create a model and to test it in a wind tunnel, it is a really expensive, and again it is a very time taking as well as very difficult task, right? So that is the reason where CFD comes into the picture, and that helps a lot in getting a solution faster and easier as well. So that is what importance of the CFD, what we can say. And then how does this CFD works? So I'm just talking in general. If you are really willing to understand it thoroughly, then you can refer a book that is CFD by JD Anderson, which is one of the good book for the CFD, right? So you can just refer that, and definitely that is going to help you, right? So how does this CFD work? So you can see this is a general transport equation which is derived from the Navier-Stokes equation, right? So it has this unsteady term, convection term, diffusion term, and the generation term, right? That is the source term. So it solves this complete equation for each control volume. What is control volume? It is the element or cell of the complete fluid domain. So it solves the equation for each control volume, and that is how we get a complete detailed distribution of the result throughout the model over here. Okay. Now, how we need to solve a problem in CFD, right? So to start a problem, not even in CFD, in mechanical or in any general practices, if you see, if you wanted to solve any problem, so there are three major steps. First one is a pre-processing, second one is a processing, and third one is the post-processing. So what exactly happens in pre-processing? So in pre-processing, we get a complete, understanding of the problem first. Okay. So that means we need to define the goal. We need to define what exactly we are expecting from that problem, right? So that is our first step, that is defining the goal. That comes under the pre-processing part, right? So in the goal, what kind of results we are looking? Either we are looking for some pressure change or mass flow rate change, or some temperature velocity distribution, or some velocity at the outlet, or some other result, right? Maybe drag force, lift force. So these could be our the results that we are looking from that particular simulation, right? Then what kind of model modeling option we are going to use over here? We need to simplify the model first of all, right? So how we can simplify it by either considering the symmetry or periodicity. Okay. And by taking the different assumptions over there, right? And again, what physical models that we need to be included in the analysis, that also we need to understand. Another thing is what degree of accuracy solution we need. Means like how much accurate solution we need, that is also very important to understand, right? Because depending on the solution accuracy, the time taken for the solution will be more, right? And if you are not interested in the accuracy, you just interested in the approximate results, then you don't need a higher accuracy solution, right? Then the time taken will be less. So depend these are interrelated things, right? Then depending on that, how quick or how faster, or you have sufficient time to get a more accurate solution, that also we need to understand. Then whatever the CFD tool you are using to solve that particular problem, whether it is an appropriate tool to solve the problem or not, that also we need to understand over here, right? Then second step, that is defining the domain that we are going to use. Okay. So we need to identify that particular domain. Okay. That which we need to create to solve this particular problem. So what should be the domain? It should not be too smaller that we will not be able to get a completely developed flow inside that model, or it should not be too larger as well, so that we'll not be able to like we'll be getting unnecessary mesh count, right? That should not happen. So it should be sufficient enough to get a capture the proper result, that's all. It should not be too larger as well. So Again, whatever the boundary we are going to add, or whether we can simplify that model for 2D or axisymmetric problems, and is there any other thing we need to do to apply the boundary conditions? All those things we need to understand first. Okay, once we identified the domain, what domain we need over there, then we need to create a solid model for of that particular domain over here, and then we need to extract the fluid domain out of it, right? So let's say if you see here, this is a CAD model we have, or CAD part we have. So first of all, we need to simplify the geometry. How we can simplify it? By removing the unnecessary features. Maybe if there are certain fillets, bolts, chamfers, these things are there. These are the features which are not at all takes part into the simulation, right? But they are, or they're they will be unnecessarily decreasing the mesh quality. So we can neglect those parts, so that will help you to simplify the geometry, and then we can easily apply the various boundary conditions, right? Again, if it is required to split the model so that we can apply the boundary conditions to specific domain, that to be created, right? That also we need to understand here. And then the next step is to design and create a mesh. Once you have created a model, CAD model, and once you have extracted the fluid domain out of it, then you have to define a good mesh for that particular model, right? Again, what kind of mesh we need, how we can go with the mesh resolution, whatever the computational power we have to solve that particular problem, that also we need to understand how models, physical model we are going to use for that also we need to understand, whether we are going to create a conformal or non-conformal interfaces, that also we need to decide over here. Again, what kind of elements we are going to create it. If it is a simple problem like this, then we can go with the hexahedral elements, or if it is a difficult, then we can go with the tetrahedral elements, also depending on the complexity of the model, right? So all those things we need to understand, and then we need to define the solver settings. Okay, so next step is to set up the solver, right? So in this, what we exactly do is we define the material, we define the material properties, then we define the physical model that we are going to use. It may be turbulence model, combustion, multi-phase, radiation model, that heat exchanger model, battery model. So depending on the problem, we need to define various physics model. Then we need to define the operating condition. So at which condition we are carrying out that specific problem. So maybe at you know temperature which is not a room temperature, or if it is something higher than the room temperature. So all those things we need to understand. Then we need to describe the boundary conditions. So let's say if there is some pipe where we need to define the velocity at the inlet. Let's say there is water which is coming from the inlet at a velocity of, let's say, 5 meter per second. So you need to define that boundary at the inlet. So these are like, what are the boundaries are there that you need to define, and then you have to provide the initial values, you know um, or any or the previous solution to solve that problem. What is initial value over here? Now, what are the simulation methods are there? These are the approximation method, these are not the exact method. So whatever the result we get over here, these results will be the approximate results, not the exact results, right? But to solve these equations, right, we need to provide certain initial guess values, right? So from those given initial guess values, it will solve the problem, and then we'll be getting results. Okay, so that is how it works in a iterative manner, right? So let's say whatever the input data you have given, like that means what are the temperature, then inlet boundaries, everything you have given, right? So those will be treated as a initial values, and then after that it will solve the problem and will be getting a result. So from whatever the results we are getting, from there it will be again generate or calculating a new initial values, and from there again it will solve the problem. So it is a completely iterative method to solve the problem, right? it works in a iterative manner, right, where again it will be continuing the solution until it will be reaching certain convergence criteria. So that we need to set up in the solver controls. Like let's say the solution accuracy, what I need is it should be 10 raised to minus power 6, 10 raised to minus power 7. So that high accuracy solution you need, right? So until it will reach to that solution, it will be keep on going, it will keep on going for further iterations, and then when it will reach to that particular accuracy, then it will converge the solution and we'll be getting the final result. So that is how it works. So you can see, whenever we are solving a problem, and let's say for from the first initial guess value we got a solution, right? And from that solution we like the software calculated a new initial guess values, and then again that is kept into this equation and got the results. Now whatever the difference between the results of these two successive iteration, that is called as a residual. And you can see you will be able to get that residual plot when you are solving a problem in the Ansys. And when I am saying I am giving certain accuracy of the residual, that means I want this residual accuracy to 10 raised to minus power 5 6. What it means, the results when it will be getting a constant result after each iteration, that accuracy we are defining over it. It's like up to 10 raised to minus power 6 decimal, there won't be any variation in the result. 10 raised to minus up to 10 raised to minus power 7 minus power 8, something like that, you need to define that value. So whenever it will reach to that particular accuracy, you will be getting a convergence. Okay, and that is how you will be able to solve the complete problem. Now whatever we have defined till this till the boundary conditions and everything, that is your pre-processing part. In the processing part, we give the solver setting and solve the problem. Okay, and in post processing we analyze the result. Okay, we examine the results and get the solution. That is how all these three major steps are there: pre-processing, processing, and post-processing. So in the last part, that is in the post-processing, when we are examining the result, we need to find check observe the flow pattern, how the flow is getting separated, or how where does this shock layers or shear layers are getting formed, any other flow features, those are being resolved or not. We can find out the different numerical reports, like we can get a force data or momentum data. We can find out the heat transfer coefficient, flux balances, surface and volume integrated quantities, that we can understand whether we find that these are in a a specified limit. Like that idea you will be getting over the practice, right? You'll be able to understand whether yes it is correct or not, right? Once you understood, if there is some problem with that, we need to do a cross questioning. If we have solved problem in 2D and there should be certain effects which will be there in 3D, so that also we need to understand. If we have solved the problem with a steady case, and if we need to solve it with the help of unsteady, what are the flow is there, if it is a turbulent flow, are there certain compressibility effect, all those things we need to understand. You need to do a cross questioning. What are the values we got, boundary values, and other boundary conditions we are given, all those are appropriate or not, all those things we need to check. Even we need to check whatever the mesh we have created, whether it is a good mesh or not. So all those things are interrelated, right? So once if anything is wrong, then you need to go back to that particular step. You need to update the data. Maybe you have not you don't have a good quality mesh, then you need to go back to the mesh again, define a good mesh, and then again solve the problem. Likewise, it is a complete cycle until you are getting the result. So that is how the CFD works. That is how you need to take care of all the parameters, then only you will be able to get a more accurate solution. Okay, so I hope this is clear to everyone. And with this, like I have completed the introduction part. So is there any question in this? Okay, so I feel that is completely okay, right? So I think we can stop over here. what we'll do is we'll take a break, and then we'll again be back at 2. Then I think now it is coverable, so we can start to solve the problem after the lunch break. Yeah. And I'm sorry if anything is going in a faster way, but then only I will be able to complete the syllabus. Anyways, if you have any question, any doubt, you can ask. Anyways, the recording is going on. I'll be sharing you the recording of all the sessions. Okay, so there won't be any issue with that. Yeah. Any doubt?
Yeah, Kailash, we are good from our end. So we'll restart the session at 2 p.m. gentlemen after the lunch break.
Yeah.
So, oh, Kailash, the speed was okay, right? I think the participants also understood what you are referring. So that's okay.
Okay, fine then. And in the meantime, I don't know how much is your lunch break time. So you can just take a time and practice the meshing part. You can just start with the mechanical. You can solve a simple, one simply supported beam problem or something like that. Okay. So that will again help you to understand. And just now I have explained, so you can recall the things easily. So just try it out. And if you get any difficulty, you can just ask me around, no, in the second session. Okay. Okay, then we'll meet at 2. Yeah, thank you. Hello.
Hi, Kailash. I think we are good to start.
Okay, sir. Yeah. So we'll start. So I hope you got the idea about the steps of the simulation. So what we can do is now I will start one problem from start to end so that you can get a complete idea how we need to deal with any CFD problem. Okay. So let's start. Okay. So here, wait, I'll just share the screen 1 second. Yeah, I'll just take a new. Okay. Yes. So for CFD simulation, we need to take a a fluid flow fluent analysis system. Okay. So we will take this complete analysis system and then we'll do the analysis. Okay. So for mm, drag this fluid flow fluent analysis system and drop it over here. So here, as you can see, these are the steps which you need to follow to complete a CFD simulation. So first is geometry. So just click on geometry. Okay. It's launching the Spaceclam where we can create the geometry. Okay, so it's launched. Now here what we need to do is we need to create a model. So here what we are going to do is we are going to add a we need to add this uh, we have to add a CAD model first. So what we are going to do is we are going to simulate a flow of water which is entering we are going to create a T section pipe. So there will be two inlets and one outlet. So what we are going to do is we are going to simulate a flow from two inlets and out. There will be one outlet. So we are going to add a flow from inlet one, let's say at a velocity of 1.5 meter per second and at a temperature of let's say 303 Kelvin. Okay, then from inlet 2 we are going to add a or the flow will be or water will be coming at a velocity of let's say 3 meter per second and at the temperature of 363 Kelvin. The pipe surface will be at a temperature of 343 Kelvin, and then we are going to understand what is the temperature distribution throughout the flow, how mixing is going to take place, how heat transfer will happen when both the streams will mix together, and how heat transfer will take place from pipe towards the fluid side or from fluid towards the pipe side, and again what is the temperature at the outlet and what is the velocity at the outlet. So these are the our goals, or what this is what we are expecting from this simulation. So this is a first step, that is to define a goal, and second step is to identify the fluid domain, so and creating the
extracting the fluid domain, right? And then creating a mesh for that, and then applying the boundary condition. So these all are the pre-processing steps. So first we have decided what exactly we are looking from the simulation. Now we'll create a model. I'll just create a sim model and then I'll explain again the problem statement. Okay, so this is the pipe. I'll just turn to 3D mode, select the face and pull on both sides. Let's say we'll give dimension of 400 mm, and then again create a circle on this on the perpendicular plane to this. Okay, so this is the perpendicular plane. Let's say we'll create it at um, minus 75. Okay, and it's of 27 mm diameter. Okay, return to 3D and take a pull command. Select this surface. From now it is inside this section, right? You will not be able to get it, so you can select from the structures view. Okay, and then click on add material and drag it down. Let's say we'll give it as 100 mm. Enter. Done. Now make it a hollow pipe. Use shell command and delete the inner volume fill material. Okay, so we can see the thickness is 1 mm for this pipe section, and pipe is created. So what is inner diameter of this pipe? So we can measure it with the help of measure option, or you can simply use shortcut key, that is E. Okay, that will also activate the same command. So click on inner surface, you can see cylinder diameter is 30. So inner diameter is 30 over there, and here it is 25. Okay, so we have created a CAD model. Now from this CAD model we have to extract the fluid domain, right? So go to the prepare volume extract, select the edges, okay, and select all the inner edge loop of the all openings. Okay, select this as well as this. Okay, all edge loop openings have been selected, so just say okay, it will create a volume. Okay, so we can say this is a, I can rename this as a fluid. Okay, and this is the pipe. Rename. Okay, so we can say um, the pipe. Okay, this is the pipe section and this is the fluid section inside the pipe. Okay, so we have successfully extracted the fluid domain, correct? So I hope you got the till this. Now we don't need the pipe section. Why? We are not going to take we are just going to take its effect in which is a temperature effect, right? So for simplification, it is okay if you take a pipe, then there will be we are that can be considered as a wall surface, but it is okay if you don't take a pipe, then also we can have a effect of a pipe. Okay, so for that purpose we don't need a pipe. So when you don't need it, you need to suppress it. Okay, so right click on pipe section and click on suppress for physics. So that will with this sign you can say it will be suppressed, and that will not take part into the further simulation. Okay, what it means, it is available, it is not available for the further simulation. But whether we can delete this instead of this, yes, you can delete it. But what is the disadvantage of deleting? If you delete it and if you wanted to make certain changes afterwards, you need to recreate that model again. But here when it is suppressed, you can again activate it for physics, and then again it will be there, so that you can again use it for the further changes or anything required. Okay, so that is the reason we do suppress this. Okay, okay, it is suppressed, and now we can say only complete fluid domain is there, correct? Go back to the workbench and launch the mesh where we can create a mesh for this. Okay, so model is imported. Uh, Done. Once the model is imported, now here we won't get any material here, right? For the CFD problems, we do apply the materials in the fluent itself. We don't apply them, you know, somewhere outside. Okay, so we don't need to um, create the material inside. We don't need to add the material in the engineering data, and also all those options are not available here. Okay, so going back to this again, now what we need to do is we need to create a mesh over here. Okay, so here also you'll be able to see this only volume fluid. I'll again rename this as fluid only. I don't want that as a volume fluid. Okay, also this is the fluid domain that we have. Now we need to create a mesh. Now one thing you will observe that when we have selected the mesh over here, physical preference will be by default CFD. Okay, why? This is why, because we have taken a fluid flow fluent analysis system, and that is the reason software now we are going to take this mesh for CFD only. So here by default preference is given. So those preference will be changed only when you are taking a component system, like you are taking a geometry, then adding the mesh to that, this mesh to that, then only you'll be able to see that option, which is a default, that is mechanic. Okay, so here no need to be worry about it. Just create a mesh. So let's say I'll give a element size of 3 mm and generate a mesh. Okay, so mesh is created. Now observe the mesh. Still need to be refined, so let's add it little smaller sizing and refine the mesh. Okay, mesh is refined. Now we have seen one specific option yesterday to capture the boundary layer formation. What is that? Inflation layer. So go to the mesh, insert, and go for the inflation. Okay, since it is a CFD problem, there should be boundary layer formation, right, on the wall surface. So which are the wall surfaces? This surface and this surface, right? So there we need to create a inflation layer. So select the geometry first, and then in the second boundary select the wall surface or the surface of fluid which will be in contact with the wall. Okay, click on apply. Here we'll go with the smooth transition with, let's say, 6 number of layers. Right, not 6, let's give it as 4. Right click on mesh and say generate the mesh. Okay, so mesh is created. If you see the inflation layer now over here. Okay, so this is how we can get an inflation layer. And once this is done, if you want, you can take a cut section, you can check it out. So take a section plane and then you can observe this. Okay, so you can see the inflation layer is created to along the complete wall surface, right? And now next step is to create a name selection over here. So in CFD, name selection plays very important role, and it has to be done in a very precise manner, right? So to understand the boundaries, it is required to be created in a very specific manner, right? So let's say this is inlet, because see, whatever the name selection will be giving, depending on that, it will treat those as a you know those boundaries will be treated according to the name selection what we are giving. So let's say if I'll say this is as inlet, Okay, then it will treat this as a inlet. If I select this will be treated as a outlet if I name it. If I don't name it, whatever the surfaces which will not be named, those all will be considered as a wall surface by default. Okay, so that is the reason it is preferred to give the name selection, which will help you to get a faster mesh. Okay, so select this face, and to create a name selection, right click and create name selection, or you can use shortcut key which is N. Okay, so create name selection, and we'll name this as a inlet 1. Then here you can see this name selection will appear over here. And then next step is select this face, again create name selection. This is inlet 2. Okay, and then the third one is outlet, right? So select this. Okay, select this and again press N shortcut key, outlet. Okay, done. Now this is a wall surface and this will also wall surface. So we can name both together. So select both and press N, name it as wall. Okay, if I don't name all, then also it will by default creating a name for that as a wall. Okay, but just for understanding, I'm creating it. Okay, so you can see inlet is created. Okay, then inlet 2 is also created, and then outlet, and then wall surface, right? One thing here need to keep in mind that do not name two different surfaces, any surface twice. What I mean is, let's say you have named this as a inlet. Okay, inlet 1, and by mistaken you skip selected this and this also, and then you name this as a wall in the wall. Like, what will happen? Software will get confused whether this is actually inlet or a wall, right? So that is a wrong name selection, and when you do such kind of mistake, it will not even launch the fluent also. Okay, so that thing you need to keep in mind. So you should be careful while selecting or creating the name selection. Okay. Okay, so just once it is done, go back to the workbench, and now you can see your model is or mesh is done. Now one thing what you need to do here is you need to I'll just delete this. I don't need this. Okay, you need to update the mesh. You can see it is showing this update sign. So right click on mesh and click on update. Then only it will share this mesh with the Fluent. Okay, you can see it is updating, and once you get a green tick, then you are good to go for the setup where you can apply the boundary conditions and solve the problem. So this is the Fluent setup. So double click on it, and you can see on the bottom side it is showing starting Fluent. Okay, so first of all we'll get a window that is Fluent launcher. Okay, so this is a Fluent launcher that we have over here, which is in 3D. Okay, by default it will sense the geometry. Now it is 3D model, so automatically it has taken that as a 3D, and then you can enable the double precision for better accuracy. Okay, and then we have this solver processes. Okay, uh, then we have the solver processes where we can give more number of cores depending on your system. So to find it out, you can just go to the task manager, and there in the performance you can check out how many number of cores your system is having. So here you can see for my system I have 4 cores. You can use 4 cores. Any though you have more number of cores, but again depending on the license what you are using, number of cores will be changing. Okay, so that also you need to keep in mind. So like if teaching license is there, that will have only 4 cores. Okay, so you can use up to 4 cores. That is also more than sufficient for the teaching purpose, so no issue with that. Okay, and research license comes, I think it comes with a 16 cores, so that is also advantage with the research license. Okay, So done. We have set given 4 cores, and here you can give the working directory where you wanted to save the file. Okay, so we'll go with the default one. Just click on start, and then it will launch the Fluent. So here you can see starting Fluent. Okay, so you can see this Fluent window, and Fluent is launched now, and we can start applying the settings over here. So here, first setting that you can see here is, let's see the GUI over here. So GUI is something different from the mechanical GUI over here. Okay, so you can see this is the graphics area where we have the model. Then on the bottom side here in the console we can see the various commands performing any TUI, like a command. If you want to run it, you can type it over here, or whatever the error message, everything, or progress of this solution, that you can track it over here. You can get a warning messages over here or error messages over here. Okay, you can easily track that. Okay, then this is the outline view. On the left side, what you can say, which we need to follow to complete the simulation. Then on the task page, whatever you can see, these will be like details in the like mechanical, we were selecting mesh, then we are getting details of the mesh. Same way, whatever we are selecting here, we'll be getting the details of it in the task page. Okay, then same options are available on the top side, different in the different tabs. Okay, either you can use from this or from this, and you can complete the simulation. Doesn't matter, there are few additional options which are available over here, but as per the requirement you can select. Okay, but most of the times these options are more than sufficient to solve any kind of problem. Okay, so first one is the general settings. Okay, so we can start with the general setting. Okay, so in the general setting, first option that we have is a mesh scale. Okay, so here we can scale the mesh, scale up or scale down the mesh as required. We can change the scaling factor, and we can change the like a scale the model. Okay, if you don't want it, just change the units. Okay, convert units. I want to change the unit for length to mm. Say okay, apply and close. Now, one more thing you might have observed everywhere, this question mark, or if you go over here, here will be help option. If you go to the meshing here, when you take a cursor somewhere, if you don't understand what that option exactly is, what you need to do is take your cursor over there. Let's say I don't know the mesh and I want to understand what all the options are there. Take mouse cursor to that and press F1. That is no, F1 from your keyboard, and it will automatically launch the web page, and it will direct you to that help page where you can easily understand those things. So here you can see, here you'll be able to see this complete mesh settings, everything. Now this is related to name selection. If you want to know about mesh, anything, you can just need to press F1 there, and it will automatically take you to that you know to that web page. Okay, so likewise you can go for it, and you can get a help, and that will be helpful for you to understand the various options. Similarly, from the Fluent also, let's say this scale mesh I don't know, then just click on help. It will also redirect to the web page, and there it will explain you all the details. Okay, so this is the way you can understand. If any point or any option, if you are not able to get it, you can just directly use the help option. Okay, then um, here also you can see this question mark. You can even click on this will also redirect to the Ansys help page where you can learn this. Okay. And this Ansys customer portal, this access is free for all the customers, so you can take a benefit of this. There you'll have a lot of content which you can download it. Let's say whatever the content I have shared, the same kind of content you can get it over here. Let's say I want to get a content for the Fluent, so just click on the Fluent over here. You can see in the filters you can go to F section and here launch the Fluent. So here you can see you have the multiple tutorial files, various videos, and the other user guides. Everything is there. It is in a PDF file format. You can easily download this and take a a reference of that for any kind of simulation. Okay, so all those things are very easily possible over here, and you can easily do that. You just need to click on download, and you can easily download this tutorial files. Okay, it is again same tutorials and the required files to perform that tutorial both are given over here. Okay, so that also you can do it, and but for this you'll need a login. Okay, so you need to create this login from the no when you try to register in your license file, there will be a customer ID, okay, or customer number. So if I think if you show it to sir can explain you where is that customer number, and you can easily you know you can easily use that number, and you can create login for yourself. For one customer number you can have multiple login, doesn't matter. If you anyone wants to create his individual login, you can create it. Okay, so that is also available. You can have help from this for the various options. Okay, so those things are easily possible. Okay, so then next step is to check the mesh. Okay, when you click on mesh, it will show you the complete mesh details over here. Okay, you can see it's showing checking mesh and it is done. Okay, then then once this is done, then you can see the mesh quality. When you check the mesh, you should view the mesh quality